This is lecture 6-7, and it's all about solutions, how they're created by intermolecular forces, and how we separate them using distillation and chromatography. This is the last lecture of this unit, and it kind of brings us full circle to understanding how behavior of chemicals is related to their structures. So make sure that you do the learning targets first, as usual. And then you can restart the video. So pause the video now and restart it when you're ready. Okay. So, excuse me. So something that we need to talk about with solutions is how the solutions actually form. And we've hinted at this a few times as we've gone through the year already, but basically the way that the solution forms depends on who the components of the solution are, depends on the nature of the components of the solution, whether they're ionic or polar covalent, etc. So as you went through your learning targets, you should have decided what kind of intermolecular forces or what kind of attractions were included in different types of solutions and whether they would actually dissolve or not. So this is kind of going to be a brief summary of that as we go through here. So the solvation process is the process of particles breaking attractions with particles that are like themselves and forming new attractions with particles that are not like themselves. So basically, anytime something dissolves, the attractions that are holding it to itself and the solvent to the solvent have to be replaced with new attractions between solute and solvent. And usually the solvent is present in a lesser quantity. The solute is present in a lesser quantity than the solvent. And so in some things where the amount really doesn't matter, then instead of talking about something being soluble in something else, we talk about it being miscible. And you should have defined that word as part of your learning targets. So I want to kind of break this down into different types. So what happens is that if we have an ionic solute and a polar solvent, so this would be like an ionic compound in water. It could be other polar solvents like alcohols or even other polar liquids, but usually in this case, most often we're talking about water. If we have an ionic solute, that's a really strong attraction between ions here not those ions, those are the negative ones, but between these ions and these ions in 3 dimensions here, we have lots of attractions. And so this is a really hard crystal, remember. And then in water, we have the attractions that form as hydrogen bonds between the hydrogen of one and the oxygen of another, right? So we would have all these different attractions that are forming here or that have been formed here in our solvent in the water and in our solute in the ionic compound. So what happens is that the positive end of the water molecule ends up attracted to the negative ion and sneaks in between. You want to kind of picture that in order for this to occur, the solute molecules sneak in between the solvent molecules and the solvent molecules sneak in between the solute molecules. And it's going to always be the positive forms a new attraction to the negative region of the other. And so this is what we call ion dipole attractions, because we have an attraction eventually between an ion and the pole of a dipolar or a polar molecule. So it's just literally this process of breaking old attractions, breaking the old ionic bonds and forming new ones. If something dissolves, it means that the attraction between solute and solvent is stronger than the attraction between solvent and solvent and solute and solute. So you have to kind of keep that in mind. It's a lower energy state. So those attractions would have a greater amount of potential energy to be broken once they've been replaced. So breaking the attractions of the solute to solute and solvent to solvent requires less energy than is given off when the new solute to solvent attractions are formed. Keep that in mind, okay? The other thing that I want to think about here is that as we're talking about this, ionic solutes then and nonpolar solvents are not usually successful because the nonpolar solvent doesn't have the positive negative end to allow it to sneak in between. every once in a while we'll find an ionic solute that is soluble in a nonpolar solvent, and this would be because the ions can create induced dipoles. So remember that this was a part of what we talked about as London dispersion forces, that induced dipoles are when the perhaps negative end of a polar molecule bumps up against a nonpolar molecule and repels the electrons to the other end. It creates that positive end in the region that's closest, and then they're attracted to each other. So this can happen, but it's rare, and so you're not going to be looking for it. You would, if someone gives you something that you don't expect, like an ionic compound actually dissolves in a nonpolar solvent, then you would want to make sure that you're using this as your explanation, but we're not going out looking for them. So usually we say that ionic solutes are insoluble in nonpolar solvents. It's a little bit different with molecular solutes because we have to worry about nonpolar and nonpolar. The statement like dissolves like means that two things that are nonpolar will be able to dissolve within each other. But the attractions are all weak. They're all London dispersion forces. So really what's going on is that this is because of not really strong attractions, but because of random mixing of the particles. So you have to picture that if you're a nonpolar solute and a nonpolar solvent, you might be weakly attracted to the particles around you, but someone else can very easily come in and replace that attraction, even if it's a weak London dispersion force attraction. So, of course, shaking or stirring speeds up any solution process, but it would definitely speed up the process of nonpolar to nonpolar. And this is a soluble situation because there's not really having to overcome really strong attractions in order to fit in between. Polar solutes and nonpolar solvents usually do not work because the polar solute is too attracted to itself for the nonpolar solvent to break into that attraction. So you want to kind of picture it that way. All right. And so it's kind of the same idea that if they are, and somebody gives you a case where you're going, wait, this is polar and that's nonpolar, why are they dissolved in each other? Then it's because those polar molecules can create induced dipoles just the same way as they would with the induced dipole and London dispersion forces that we talked about also with ion dipoles. Again, don't go looking for it. If you're asked, you're going to assume that polar solutes and nonpolar solvents or polar solvents and nonpolar solutes are going to not dissolve in each other. Only if they tell you otherwise are you worried about induced dipoles. I do want to talk a little bit more about polar and polar because this is now kind of like ionic and polar, that we're looking for those new attractions that would form. So, dipole-dipole interactions are just simply positive-negative regions. I do want to talk a little bit about how on this alcohol that we see right here, that this end is polar, but this end is pretty much nonpolar. Okay, and so that's related to what we'll discuss in a few minutes, but this is something that the larger the alcohol, the more there is a non-polar part of it. And so that definitely affects alcohols and carbon organic compounds and the way they dissolve. So even if they're polar, sometimes they don't dissolve very well in polar substances because they're just too long. So we want to talk about that as well. But you can see that, like, if this is the negative region of this alcohol, then this water molecule is going to spin around so that the positive region of the water molecule ends up attracted to it. And that's kind of what's going on here then, is that this positive region of this water molecule is going to have to spin around because now this is going to be the positive region of the alcohol. And that would allow those attractions to replace the attractions between alcohol and water and water. If it's hydrogen bonding, then this is even better because hydrogen bonds are just strong dipole attractions. The more capability for hydrogen bonding, the more soluble another hydrogen bonding substance will be in it. So alcohols, that oxygen has two places here where hydrogen bonds can form, and so does water, two places here and here where hydrogen bonds can form, like so, between molecules. And so again, the more like you are, the more those attractions are likely to form, okay, based on energy differences more than anything else, potential energy differences. So just kind of remember that as you're going through here. I did hint at this, and I do want to talk about this. Your book spends a lot of time talking about it, and I put it in your learning targets because I think it's important for you to know that, yes, alcohols should be soluble in water because they have this, which would allow hydrogen bonding. And water, of course, has the same thing, which would allow hydrogen bonding. And so this should be easy for them to dissolve in each other. Methanol will be very soluble in water because it's small, and so overall the molecule is really polar. That this would be your hydrogen bonding negative part here, and then this, and then this non-polar portion of this CH3 actually is pretty small, right? But here we have this spot on pentanol where we're able to create hydrogen bonds, but then notice that this non-polar region is really long. And so picture that if this were trying to fit in between water molecules, you might be able to get a water molecule here, you might be able to get a water molecule here, but this region right here isn't really going to be able to reach in between water molecules and break the existing hydrogen bonding that's holding the water to itself. So the longer alcohol or organic chains get, the less soluble they are. And you want to picture that in water, right? The opposite is true of nonpolar solvents because they are so nonpolar. They just kind of randomly are more likely to be able to fit in and make new London dispersion forces. So that's just something to kind of keep in mind as you're looking at things. Finally, separating solutions is something that you've learned a couple of different ways. Remember that we will, if we haven't yet, and if we have already, that we have looked at the still in our chemical prep room, in our chemical stock room, and we talked about the process of how that happens. But remember that distillation uses differences in boiling point and retains the substance that evaporates more easily, because it's what's going to evaporate first and then will be condensed, okay? So the process is heat up whatever your mixture is. The one that evaporates first will evaporate and rise. It will go down this tube, and this is surrounded by cold water. So inside this tube, it will condense and drip out the other end. And the substance that doesn't evaporate as easily will then be left in the flask. Okay, so this is one way of purifying and retaining the one that is more volatile. Keep that in mind. Okay, column chromatography is what we're going to do in the lab, and so this is where you have a mobile phase that's moving. Typically, it's a solvent like water or alcohol or acetone or something like that, and then you have a non-mobile phase. We call it the stationary phase. That is trying to stop the movement of particles. And so in column chromatography, you actually put in your thing that you're trying to separate into the column, and you want it to be attracted to the column so that the solvent that you put in has to break those attractions and pull it off, right? So we can use one solvent at a time, and this is what we're going to do in the lab, and I think you'll understand it better after that. But I did want you to just kind of get an idea. Most of you have done paper chromatography where you had your piece of paper maybe in strips and you put a dot of ink on it. That's a bad way to draw that. So maybe you had your piece of paper in a strip and you put a dot of ink on it, or you dotted a pigment on it, and then you set it down in a beaker that has a liquid here, and the liquid, because of capillary action and adhesion, will rise up the paper, and then as it goes, it will come through this pigment and start to carry the pigment up the paper. And what happens is that pigment is more attracted to the stationary phase, or to the paper. It will travel slower, and the ones that are more attracted to the mobile phase, or the solvent, will travel faster, and eventually they'll fall out when they're slower and more attracted to the paper. So what you end up seeing is a series of places where these pigments have separated out, and so we've done that on paper. We're going to do that now in a column, and it works very much the same way. The stationary phase is just the solid packed in the column, and then your solvent either forces this through or forces it part way through where it's kind of still attracted to the column, etc. And you'll see how this works when we do it in the lab. But notice, most important, that chromatography, any chromatography, is based on the attractions between whatever it is you're trying to separate and the solvent versus the attractions between whatever trying to separate and your stationary phase. Okay, and so the more attracted that is, the more mixture, the more likely the mixture will go on through. I think I shouldn't have said solvent here. I should have said mixture, or the components of the mixture are to the mobile phase, it will pull it down, and the more attracted the components of the mixture are attracted to the stationary phase, the slower it moves. Sorry, that's a typo. I will fix it later. Okay, so that gives you an idea of what's going on a little bit with solutions and how we separate them. And hopefully that was helpful.